Welcome to the third lab in our error detection and correction series. In this lab, we're going to learn to calculate checksums. When we learned about parity, we used a single bit to check a number of bytes. Checksums work by using a single byte or a number of bytes to check a number of bytes that are part of a block. So it's a way of checking larger units of data. On the next slide, we're going to talk about how they work. A checksum does exactly as its name implies. It's a sum over a number of bytes that's used to check for errors. The way it works is that you have a number that is used and compared between a sender and a receiver. If that sum over all the bits is the same, then there have been no errors. The checksum can be represented by a number of bits. So if you have an 8-bit checksum, your sum, the number that you can send and compute, is 8 bits. And with 8 bits, we have a range from 0 to 255. However, when you take the sum over a large number of bytes, that sum can be larger than what you can represent. So, how do we deal with that? Well, we deal with that by using a modulus operation. So a checksum is that sum mod a particular number, and that number is determined by the number of bits in your checksum. Okay, the range of values that your checksum can represent. Again, the way this works, the transmitter goes over its data bits, takes the sum takes it that mod a number depending on how many bits are used to represent that checksum, and it sends that number. The receiver then computes the same checksum on the data bits and compares its computed value to the received value from the receiver. If they're the same, there's been no error. Again, there is a possibility for multiple errors canceling out and getting the same checksum, but for the most part, that's an unlikely situation. However, if the checksums are different, then there has been an error somewhere. There's a difference between the data sent by the transmitter and received by the receiver, and the checksum shows that there's been some sort of error, usually due to noise. Let's look at an example. Imagine we have a block of 8 bytes, where 7 bytes are data and the 8th byte is the checksum. We have 1 byte to represent and use in the checksum. 1 byte can represent a range from 0 to 255. So the modulus operation used to compute the checksum from the sum would be the sum of the 7 bytes in the data mod 256. Now why 256? Well, that's 1 plus, okay, the maximum number that you can represent with 8 bytes. So the maximum number you can represent with 8 bytes is 255. So add 1 to that and you get 256. To compute the checksum, you need to take the sum of the first 7 bytes. Imagine that these 7 bytes are the ASCII characters in a word. So yogurt, for example. So Y is hex 59. O is hex 6F. Okay. When you take the sum of all of these hex values, on the next slide you'll see the complete calculation, but the result is hex 2F2. You need more than 8 bits to get the sum. We can't transmit that in the 8th byte. So we use this modulus operation Now, 256 in decimal form is the same thing as hex 100. So when we do that, when we take the sum is 2 hex 2f2 mod 100, the result is f2. Really what we've done here is we've taken the last two nibbles of the checksum sum, right? The sum, the 2f2. We've just taken the low order f and 2 bits. The sum from the hex values that make up yogurt are added up one at a time. So we have y plus o, so it's hex 59 plus hex 6f, gives you hex C8. Let's take a look at just the details of this addition operation. So if we look at the last column, 9 hex 9 plus hex f. F is 15. So 9 plus 15 is 24. 24 minus 16, right? Because how many 16s do we have? We're going to carry. That's 116. So we carry that into the second column. We carry the 1. That's 116 into the next column. And what are we left in the first column? Well, we're left with 8, right? 24 minus 16 is 8. So we put the 8, carry the 1. Then we look at the second column from the right. 1 plus 5 plus 6 is 12. 12 is represented by C. So the result is 0, C8. And we take the hex C8, right? We add that to G, and we continue on all the way through T until we get 2F2. And we'll continue with the mod operation on the next slide. So we see the sum is 2F2. Okay, the mod operation is 1 plus the largest value, right? That's what we're going to take the mod with of 2F2 mod hex 100, right? Just to remind you, whenever we want a random number between 0 and a, we take that random number mod a plus 1. And that will give a random number between 0 and a. You may have seen this previously in early C courses. So that's where this comes from. So again, this modulus operation basically takes the low order bits, because 2 mod 0 is 2. F mod 0 is F. 2 mod 1 is 0. So 2F2 mod 100 is F2, which is basically taking the low order bits. Now, an alternate operation that you can use instead of mod is bitwise AND. Now, in this case, you have to take the bitwise AND with FF. Remember, setting those last bits, if they're F and F, they're all ones. So we are ANDing with only those low order bits, so this just takes the low order bits. See, 2 and F, it's just going to give you 2, because 1, right? 1 or 1 is 1, 1 or 0, or sorry, 1 and 1 is 1, 1 and 0 is 0. Okay, so basically, using the AND operation is another way to take the low order bits. If we consider 16-bit checksums, then all we're doing is we're grouping our fields. Instead of having 8-bit words, okay, we have 16-bit words. What we mean by words is groups of numbers that we add. So if we had packets with 10 bytes here, so 01 is one of them, 00, F2, the last 2 bytes are the checksum field where we're going to input our checksum. So if you wanted to make a 16-bit checksum from this packet, you'd have to group the first 2 bytes together. So 0, 1, and 0, 0 become a single word. F2 and 0, 3 become F2, 0, 3, another word. And when we add them together, we add the words together in 16-bit fields. So it'd be 0, 1, 0, 0 plus F2, 0, 3. That would be the first result, and then we would take that and add it to F4, F5. And on the next slide, you'll see the rest of the operations. And then what we need to do in this case, if we want to take a 16-bit, so we can only represent 16-bit numbers, and the sum is likely to be larger. So the result of summing all these 16-bit numbers is 0, 0, 0, 2, then D, E, E, F. Okay? So that's our 16-bit. So if we're going to only have a 16-bit number, this is larger than what you can represent with 16 bits, we have to take the mod of 1 plus the largest number that you can represent with 16 bits. Okay? So it's 1, 0, 0, 0, 0. Okay? So the sum mod 1, 0, 0, 0, 0 is taking it just takes the low order bits, and that's just the D, E, E, F. So just to summarize the operations, we take the bytes and organize them into 16-bit words, and we add those words together. So word 1 plus word 2 gives us F303. Okay? The result of that operation added to word 3 is something larger than you can represent with 16 bits. So 3 and 5 is 8, 0 and F is F, 3 and 4 is 7, F and F is, so F is 15, plus F is 15, that's 30, 30 minus 16 is 14, that's why the result is E, carry the 1, 1 plus 0 is 1. Okay, so anyway, you get 2D, E, E, F as the result of the sum of these 4 words. Now that's bigger than what you can represent, so you take that sum, mod 1 with 4 zeros, and that gives you the low order bits. And that's what gets transmitted. D, E, E, F is the transmitted checksum. In summary, checksums can detect but not correct for errors in a block. It can usually catch multiple errors, but they can be fooled by bytes that may be reordered in the message. So a message with reordered bytes has the same checksum. By the insertion or deletion of 0 values, okay, that has the same checksum. Or multiple errors that cancel each other out and produce the same checksum is possible. Checksums can be used against any accidental modification. However, intentional modification to produce the same checksum would not be detected. Okay, it can't be used for deliberate tampering. And the overhead cost, okay, that a checksum costs. So if you have a 1 byte for a checksum, that single byte can be used on different sized blocks. So you can have a block that's 16, a block that's 32 bytes, and that overhead would be reduced, right? For the larger the block, the less the fractional overhead of that checksum, right? Before you begin this lab, it's important to review the following concepts. Void pointers are used to point to a block in memory with no specific data type. What that means is that the grouping of the bytes has not been set. You can cast, okay, and that's another thing to study is casting. You can cast a void pointer to a car or a pointer to a character pointer, which means that every element, okay, is taken 8 bits at a time. Or you can cast to a short integer, and each element is taken 16 bits at a time. So when you're looking at the first and second element, if it's cast to a car pointer, then the next element would be 8 bytes from the first element. However, if we're looking at a short integer, the separation between the first and second element is 16 bytes. Okay, so that's something to talk about, or to review, is pointers and casting. Also, to look at the differences between integers, short integers, long integers, car integers. They each take a different number of bits. Right? A car is 8 bits, whereas a short is 16 bits. And that's an important point for this lab. We talked about casting. You may wish to review switch statements, because we're going to require a switch statement be used in this lab, and masking bytes, which we saw in lab number 2. The goal of this lab is to create a checksum.cpp file, which contains a function, a checksum function. It's going to return an unsigned integer as the checksum. Remember, checksums can't be negative. It's going to take in a pointer to a block of data, okay, that you wish to have the checksum on. It's going to take the length, so the number of elements, and it's going to take a checksum type. And that's either going to be an 8-bit checksum or a 16-bit checksum. So the pointer to the block of data, the number of elements, and then the size of each element in terms of the number of bits per element. And then the checksum will be returned as an unsigned integer. The checksum data type is an enumerated data type that's either going to be check 16-bit or check 8-bit. Okay? And basically, if it's check 16-bit, then the items in buff are 16-bit quantities. If it's an 8-bit checksum, then they're 8-bit quantities. So buff points to a memory location. iBufflen is the number of elements of a given type, I type, or size, I type. Okay, 16 bits or 8 bits each. Okay, and basically the checksum returned is going to be sized depending on whether we choose 8 or 16 bits. Okay. For this lab, please download for the main for lab 3 from eConestoga. In main, you're going to have your main functions, but checksum, the checksum function must be in checksum.cpp. There must also be a checksum.h. Make sure you study main before you start the lab to understand what it's going to supply. And you can't change main in any way. It has to be kept the same. And you must use a switch statement, okay, to select between different checksum types. Okay, so we're going to use a switch inside our function. Okay, let's get started on this lab. Okay, so first thing we want to do is open up Visual Studio. Okay, create a new project. We're going to call it Lab 3. So we're going to make a console app. Go next, say Lab 3. I'm going to put it on the desktop. Okay, I'm going to put it right in here. Okay, and then say create. So it should create a folder here for us. It's going to build it. And the next thing we want to do is, okay, so we're not going to use the auto-generated file here. So we'll remove that one. Delete the file completely. And what we want to do is we need to go and download. Okay, let me go here. We need to download the main from eConestoga. Okay, so you're going to go and get that. I've already downloaded it. So I'm going to copy that over and paste it here. Okay, so once it's pasted there, you're ready to go with that. So let's open this up. what we need to do, we need to add an existing item, okay, which is main lab 3, add that to the project. So this is the file that you're given, okay. Now, you can already see that there's an error. The error is because we don't have checksum.h. Okay, so what we need to do is we need to actually get checksum.h. All right, so what are we going to do? We need to make it. So let's go here, go header, add. Now we're going to make a new item. Okay, and we're going to make it a header file. Say add. And in here, I'm not going to use the pragma once, okay? And I'm going to use the if and f blocks. Okay, so that this code can also be used in Linux, on the Linux side as well. And I showed you in the first lecture how to take the project and bring it over, the first lab actually. The first lab, we talked about how to take the code that we built here and run it on Linux side. I'm not going to repeat it. If you want to do it, please do. Just use the Linux side. So the first thing we want to do here is actually I'm going to make a multi-line comment. So space, enter, space, enter, space. Okay. So what I'm going to put here is the name. So it's checksum.h. Okay. This one right here, this is because it's the header file, this is our interface. Okay, so I could do this if you like. I could say, actually let me do like this. So this is our interface, okay, and this computes the 8 or 16-bit checksum on a buffer. Okay, so we're going to give it a buffer, and then we're going to say, do we want the 8-bit checksum or do we want the 16-bit checksum? Here, I could put author, okay, and then the date. You could put, whatever year it is, date, whatever. You can do that. So first thing we want to do is we only want this file to be referenced once. Okay, once it's linked to the project, we don't want it to have to do it twice. So put our if not defined. Okay, checksum h. Then we're going to define checksum h. So this means it'll only happen once. And then here we can put our end if. Okay, so this will only happen once, right? If it's not defined, define it, and what goes in between is only going to happen once. So in the PowerPoint presentation here, we saw that we have an enumerated data type, and we saw how to do this in the first and second lab, right? Enumerated data type. Okay, so we have enum, okay, and we're going to say checksum, and here we're going to have either a 16-bit or an 8-bit. So I'm going to go here, check. First one is 16-bit. Okay. The other option, so 0 is 16-bit, 1 is 8-bit, so check 8-bit. And we could, if we want for good measure, is put a check error type. Check error. Okay. And then so this is, I gotta change the name, it says header.h. But anyway, what we want here is our prototype. So function prototype, well, we might have more than one. So unsigned int is what we said, and it's checksum. Okay, we have to do this has to be exactly as defined in the PowerPoint, because this is how it's used. So we have a pointer, a void pointer, so buff. Okay, so the reason why it's void is because we can point to any data type. Okay, we want it to be able to point to any data type. So we're going to cast our data types to either, for 8-bit we're going to use cars, for 16-bit we're going to use shorts. Okay, so we have to cast it accordingly. And then we have I buff. Again, we have to follow the exact same as what's written, okay, because the main is already written for us, so we have to follow the exact, and then I type. Okay, so this is our prototype. Control S. We save everything. Now the thing that I forgot to do here is this is header.h. We need to rename it. So rename, and it's going to be checksum.h is what we need to change it to. Okay, and save. And so this is basically done. What I might want to do, so this underline is because I haven't actually defined this function. So what I want to do is actually copy up to that point, Control C. Okay, and now what I'm going to do is I'm going to create, so I'm going to say add a new item, and I want to see CPP file, say add. Okay, and here I'm just going to paste what I had here just in case. Open, close. This guy right here, what I could do is go and grab checksum.h. I can go here, say copy. Oh, I called it source. It should be called checksum.cpp. And this is not the interface, it's the implementation. Right? We have the client, interface, and implementation. The client is main. The implementation is the CPP file, and the interface is checksum.h. Okay, so I need to change this to checksum.cpp. So let's rename checksum.cpp. Okay, so these have to have the same names. The other thing I want to do is in here, this is the implementation. Okay, this is good. What I need to do is I need to include checksum.h. Okay, so include checksum.h. Okay, and the other thing that I might need, Control S. Okay, so now checksum is defined. Checksum here. Okay, this should work. Oh, because of the enum class. Okay, they want an enum class. This is a CPP file. They want the class as a best practice, but I want this to be compatible with C. So if I compile this in C on Linux, anyway, this is fine. You can ignore the enum type here error. Okay, the other thing we're gonna need. Probably we're going to need some data types. So let me include, just for good measure, standard IO dot H. Okay, Control S. Okay, so we're going to write this once we know what we're doing here. Okay, let's go to, okay, so checksum.h. This is defined exactly as we want. We don't actually need to keep this open anymore. We need main. We need to look at main and see how the checksum is going to be computed. Okay, we've got standard IO, we've got string, because we're going to have some string functions in here. Memory allocation is required, standard library is needed, and checksum.h. That's why we needed to name it this, right? We have checksum.h in the header, checksum.h here. Okay, what does main do? Main, it takes in values. Okay, it's main here. It's going to take in some values. Let's see what happens here. These are just variables. We'll look at these here later. We have, let's see here, checksum right here. So we're going to compute a checksum on a 0 buffer. So that's where this is. We've got 6 elements in here, all zeros. So we're going to compute checksum. We cast it to a void pointer. There are 6 elements in this array, and we want to do an 8-bit checksum because it's an unsigned car. Okay, so that means that each element is 8 bits. So we're going to run an 8-bit checksum on a 0 buffer. We're going to run a 16-bit checksum on the same buffer, but now we only have 3 elements, right? Because we're taking them 16 bits at a time on B0. And this is just, this checksum, they should both return 0. Okay, so that's what we expect. What else? The next thing we're going to do is we're going to run a checksum on a random buffer. Okay, so that's what we're doing here. So why we're not calc why we're not using calc is because we don't want to change the bits, set them to 0. We want to see whatever's stored in that random buffer. So in memory, we're going to go through our memory, look for a 1024-bit block that's free, okay, and then we're going to cast it so that they're unsigned cars, so they're 8 bits each, and so this is going to give us a string, okay. This is a string we call beep packed string. This is basically, we're looking at the bytes, okay, in this memory. We're looking at 1024 bytes, and we're going to compute the checksum. So what are we going to do here? We allocated some memory, right? We allocated some memory. We didn't set them to zeros. What we're going to do is at each location, okay, each byte in this memory, we're going to generate a random number, okay, between 0 and 255. Okay, that's what this is. We're using the AND operation here. We could have used the modulus if we want, but it would have to be this plus 1. Okay, so we're setting each of the elements in this array of 1024 elements to some random number between 0 and 255. Okay, and then what we're going to do is we're going to compute the 8-bit checksum on all these elements. Okay, and then what we're going to do is we're going to make some changes. Okay, we're going to make some changes to some of the bits, which is going to change the overall byte value, right? That are in these 1024 bytes. So what are we going to do? We're going to randomly choose a number between 0 and 1024, okay, or 1023, 0 to 1023 really, not 0 to 1024. I should make this correct that. Okay, and then what we're going to do is we're selecting one of the bytes. Okay, we're selecting for one of the bytes, and then what we're going to do is we're going to choose a random bit. So we're going to randomly choose one of the bytes. Okay, then we're going to randomly choose one of the bits in that byte, and then we're going to flip it. Okay, we're going to flip it from number between 0 and, it's actually 0 and 7 here. Okay, one of the 8 bits. We're going to zap. So what are we going to do? We're going to look here. So if it's a 1, we're going to flip it to a 0. Okay, if it's a 0, we're going to flip it to a 1. That's what we're using the AND equal to. Okay, so if so we have a mask, okay, is a 1, and we're going to shift, okay, we're going to shift it by I bit. Now I bit, what was I bit set to here? I bit, we're going to shift by I bit. Now I'm not seeing the I bit here. Where did I put it? Not a problem. But anyway, we're going to shift it by I bit. I'm probably not seeing it here, but anyway, we're going to shift this 1. 1 is whatever the size of mask. So what's mask? Mask is a car. It's 8. This is 8 bits wide. So it's basically 1 is all zeros, and then the last bit is a 1. So it's 7 zeros and then a 1. And then we're going to shift it by I bit. Oh, sorry, I bit is this random number. Okay, so it's a random number. So basically what we're going to do is we're going to select a random bit in the byte. Okay, and then what we're going to do is we're going to say, okay, beep packed the string, whatever that value is, okay, whatever's stored at this location at RC, okay, we're going to AND it with the mask. Okay, if it's a 1, we're going to flip the bit. If it's a 0, we're also going to flip the bit. Okay, so look, what we're going to do in order to flip that bit, we're going to take this guy. If it's a 1, we do an AND equal, okay, with whatever iMask is not. So it's going to flip it to a 0. So it's going to, this is going to basically flip the bit, okay. This also flips the bit if it's a 0. So if it's a 1, this is how you flip the bit, okay. If it's a 0, we use OR equal to flip the bit, okay. So just I show here. If the bit is a 1, then invert the mask, okay. So see, we're inverting the mask. So the 1 becomes, all the zeros become 1s and the 1s become 0. And then we AND with the randomly selected byte in that array of 1024 bytes. Okay? If it's a 0, then we OR it with iMask. Okay, so if it's a 0 and iMask is that bit is a 1, when we OR it, we flip that bit to become a 1 instead of a 0. Okay, that's all that this is doing. It's just flipping the bits. Okay, and then we recompute the checksum on all 1024 bytes, and you'll see that it should be different. Now, because I didn't seed the random number generator, everyone's going to get the same results. Okay, so we haven't seeded the random number generator, so the results that I get, it should be the same as the results that you're going to get. Okay, and then you're going to calculate, you're going to recompute the checksum, and that's going to be the output. Okay, you're going to output the new checksum. Okay, so that's all that's happening here. Okay, and that's what we expect. So we need to be able to compute a checksum. What do they expect as input? First thing is, what kind of checksum is being computed? Okay, is it an 8-bit? Is it a 16-bit? We should be able to do both. So our function should be able to do both. So first thing we want to look at is, what did they give us here? Okay, so when we start our checksum, what we need to do, what it's asking for, it says you must use a switch, right? So switch, right, on iType, right? Because this is what we're saying. Okay, what is it that they've supplied? Now switch requires, okay, this is the syntax for the switch, and then we have different cases. So we have case. So case, it's check. First we're going to do a check if it's 16 bits. Remember the syntax for that. And then at the end of that, we have a break statement. I always do this first, okay? And then I have another case. Say check. Now we're going to do the 8-bit. Okay? And then at the end, break, so that you don't forget, actually, right? And then here I have a default. And we want to do something with our default. Okay? And we want to return something. Okay? Now this is going to return an unsigned int. An int is 32. It depends on your system, but I'm going to return a 32-bit 0x1 with 1, 2, 3, 4, 5, 6. Okay. Actually, it doesn't really matter the size. I want to send a signal back. Okay, that that's an error. Okay, so this is going to be 6. Actually, total should be 6 long. Okay, I'm just going to send this as a signal for error. Okay, so that because if they don't specify, if it's not this or this, then it's check error. There's going to be an error that's generated. Okay, so let's Control S to save, and now we have to think, what do we need when so they're supplying us with a pointer. Okay, it's a pointer. It has not yet been casted to a specific data type. Okay, they're just giving us a pointer to a location in memory. And the trick here is that if we want to do a 16-bit checksum, then what we need to do is we need to cast, okay, this pointer here. We need to cast it to something that is 16 bits. Now, what's 16 bits in C? Or it's basically a short. Okay, so what I'm going to do is I'm going to say I want a new pointer. Okay, and I need to create this. I haven't yet created this. So what I want it to be, what I need to do is go up here, and I need an unsigned short pointer new buff 16. Okay, and this guy right here, this is the data type for check 16-bit. Okay, so I need that, and while I'm here I might as well do the other one. So I have an unsigned car. Okay, and this is new buff, and this one should be 8. Okay, and this is the same thing. This is the data. This is a pointer. Really, it's the pointer for 16-bit, right? It's casts. Let's say pointer for casting to check 16-bit. How about that? And then this one will be the same thing for the 8-bit. Okay, check 8-bit. 8-bit. Okay. So now what do I have? So Control S to save. Now I have new buff. This one's going to be 16. Okay. Now what I have to do is basically I have to take buff and I have to cast it, right? So I have to go unsigned short pointer, and I'm basically taking buff. So what am I doing here is I'm saying that, okay, buff is a void. It's a void pointer. I'm passing anything. I can pass anything to checksum. Okay, and what I'm redoing is I'm reorganizing the groups. Okay, right, or the words, right, which is what I used in the presentation, the PowerPoint. The words now are organized into 16-bit groups or 16-bit words here. Okay, so whatever memory location I'm pointing to here, I'm recasting to 16-bit words. Okay, now this guy is going to be different depending on, if it's 16-bit words, then these are going to be, there's going to be that many, okay, iBufflen elements that are 16 bits. Okay, so we don't have to worry. We can use iBufflen, but the first thing I have to do is cast it. Okay, because if I'm going to do anything, I need to cast it, right, to be able to know where the individual elements in this can call it an array of data, okay, in the buffer, really. So the exact same thing is going to happen for the 8-bit. However, instead of 16, I gotta cast it to 8, and instead of short, it's going to be car. Okay, so I'm casting it. So now I have 8-bit units, and now I can look at that memory location. These guys are both pointing, right? This guy's pointing to the 8 memory location, but now if I say like new buff 8 plus plus, then I'm going to the next one over, right? I'm incrementing 8 bytes over. If I go new buff 16 plus plus, I'm incrementing 16 bytes over to get to the next element. Okay, that's why I'm casting it. Okay, so now what do I have to do? So now I say, okay, I know what data type now. That's what the switch is for. Okay, I know how many elements I have, so I can use this guy when I loop through the elements, and this is the location for the memory, or the buffer memory location that I'm looking for this data. So now what do I do? Well, now what I need to do is I need to compute the sum. I mean, that's all I'm doing is computing a sum, which is really, really easy. So I need a for loop. Okay, so because I need a for loop, I need a counter, right? I need int I. Okay, this is my counter for my for loop. Control S. Okay, and I need a sum while I'm up here. So I need unsigned int, because it's the sum is never going to be negative. Okay, and then sum equals 0. Okay. I also need a checksum, right? So I'll put that in the same row. You can do this. Check sum equals 0 because it's an unsigned int as well. Okay, so Control S to save, and now I can go through my computation of the checksum. Right, I'm going to do the same thing here as I'm doing down here. It's just going to be a different type of. So I'm going to say I equals 0. I is less than I buff len, and then I plus plus, right? I'm going to go through, I'm going to increment through it. I can't use array notation, I'm going to use pointer notation, but it's not going to change much. So what am I going to do? I'm going to say I need to compute the sum first before I can do anything. So sum equals, okay, I'll do it this way, sum plus, and I started, sum always starts at 0, so I'm good. Sum plus whatever is stored. So I say star new buff, and now I'm in 16, right? Okay, so that's it. Now I can do that this way, or I could say plus equals, right? Plus equals, and then take that out. Okay, and then what I need to do, once I added it, I need to go to the next. I got to go to the next element in new buff 16, right? I got to go to the next. This guy is pointing where this guy was pointing. So I need to go to the next element. So I need to increment where new buff 16 is pointing. So I say new buff 16 plus plus. Now, that's the trick here, okay? This guy goes, so move 16 bits, right, in the buffer. Along the buffer, right? That's what this is doing, because new buff 16 was cast to a short, right? So I could say new buff 16 was cast to a short, so it will move 16 bits, right? When you increment it, it goes to the next element. Okay, now I could do this, then at the end of this, what I have to do, I want to compute the checksum, right? The checksum, after I compute the sum, right, I'm going to go through all the elements, equals sum mod, okay? Now, the maximum number that we can represent with a 16-bit checksum is 1, okay? And then we have, this is one bit, this is the other bit, right? The two zeros. This is 16 bits. Maximum would be 4 Fs, right? F plus 1 gives you this guy. Okay. Now I made one mistake. If you want to show that it's a hex, you go 0 hex. Okay. So this is my hex number. Okay. So that's the maximum. That's maximum number you can represent in 16 bits plus 1. That's our checksum, and then I return checksum, and then Control S to save. Okay. Now the only difference between this one and the next one, so I can make sure I can copy this, Control C, put that here, but be cognizant of the fact that it's not new buff 16 now, it's new buff 8. New buff 8, and now we're not moving 16 bits along the buffer, we're moving 8 bits, right? New buff 8 was cast to a character. Okay, and checksum is now, the largest number is not 16 bits, I have to take away 1 byte. Now it's 8. The maximum number you can represent with 8 bits or 1 byte is FF, right? So add 1, and that's 1, 0, 0. Okay, and you return the checksum. Okay, so that's that. The default. So that's it. That's basically it for our switch here. What we could do is we could, signal that there's an error, right? And we could say, I don't know, we could do a printf. Okay, that's why I'm going to include the standard I/O. I could just say, I don't know, say something like, you must select either an 8 8-bit or 16-bit checksum. Something like that, right? \n. And then that's it. So we just signal that there's an error and then return. So Control S to save. Okay, and that's basically it. What we need to do now. So here it's what's the error here? Yeah, the enum type. Okay, again, that's not a problem. Okay, so what do we do next? Well, we can test everything out. So let's go to main lab 3. I don't see any other real errors. Okay. We used ibit, we used imat. Well, this is we can't touch anyway. So let's run it and see. So the what we expect, a buffer of zeros. So it should have zeros here, and then we should have everyone is going to get the same result. Choose a random bit, choose a random number, and choose randomize an array of 1024 bytes. Change one of them. Change one bit in one of these. Select randomly one byte. Change. Select randomly one bit in that byte. Change it, and then recompute the checksum. Anyway, okay. So let's run it and see. We should get. You'll get the same number every time because we didn't see the random number generator. Okay. So let's take a look at the first one. What do we expect? 8-bit checksum of zeros is 0. 16-bit checksums of 0, 0. That's correct. 8-bit checksum on a buffer is 6, 6. Okay, and that's before we zapped one of the bits. And then the 8-bit checksum of the altered. Now we changed it by some value. We altered it, and the new checksum that we compute is 9, 8. Okay, this right here of the altered, right? What did we use to alter it? We altered imask. Okay, so the imask that we use, that's what this 0, 2, 0. That basically means that in the first octet, okay, the second last bit is a 1. So that's the random bit that we chose in that byte. Okay, so that's the one that we altered. In the random, we chose a random byte in that array of 1024 bytes. Okay, that's basically it. That's it for this lab. Again, I hope you enjoyed this lab and I hope you learned something. Please go through again. You can read through the comments in main. Make sure you understand what we did, especially here. You can work it out on paper. I kind of give you an explanation for it, and that's it.